Now we're going to put everything together. You're going to be doing this on your own. This is going to take a little while. You're going to have to work hard, show work, details, attention to details. That's important. Important's good. All right. We have this function, y equals x cubed minus 3x squared plus 4. Here it is already factored for you. That can save you some time. I want you to answer all of the questions about this on your packet. So go ahead and do this all the way down to actually sketching the graph. So pause the video, do that, unpause when you're ready to check all of the information. We're trying to do this with as little help from a calculator as possible. We will see some problems potentially where you're going to need to use the calculator a little bit. Like for instance here, if I hadn't factored it for you, you would have needed the calculator for intercepts. But since it's factored, they're very easy to find. So let's go through this. Domain, all real numbers. This is a polynomial. Okay. X-intercepts. Set the function equal to 0 and solve. It's already factored, so I get -1 and I get +2. Y-intercept, plug in 0 for x. I get the point 0.04. First derivative. Use this version of the function, not this, for the derivatives. So 3x squared minus 6x. Second derivative, 6x minus 6. Moving along. Find your critical values. So I'm going to factor out a 3x from the first derivative, set each factor equal to 0. I get x equals 0 and x equals 2. Those are my critical values from the first derivative. So then I can do either the first derivative test or the second derivative test. It doesn't matter. I do not need to do both of them, but I need to do one of them. So in this case, I actually showed both. It's very easy to do both in this case, or I should say either, because again, you don't ever need both necessarily. Okay, so here's my increasing decreasing chart. My critical values, x equals 0, x equals 2. I tested -1, 1, and 3. I saw positive, negative, positive. Therefore, this is going to be a relative maximum, and 2 is going to be a relative minimum. I can also see that from the second derivative. If I did the second derivative test, if I do f double prime of 0, that is going to be less than 0, which tells me that the function is concave down, which means that it is a relative maximum. F double prime of 2 is greater than 0, which means that the function is concave up, which means this is a relative minimum. So now I want to state my relative maximums and minimums using my derivative speak. Again, depending on if I did the first derivative test or the second derivative test, my speak is going to be a little bit different. Here I used the second derivative test to do my speak. It's actually just a little bit less to write, I think. So I said since f prime of 0 equals 0 and f double prime of 0 is less than 0, the point 0.04 is a relative max. So I got the 4 by plugging that back in, but actually I already knew that also because that was a y-intercept. And since f prime of 2 equals 0 and f double prime of 2 is greater than 0, the point 2.0 is a relative min. Okay, so that was the maxes and mins. Now I want points of inflection. So I have my second derivative. I set that equal to 0 and solve for x to get my possible point of inflection of x equals 1. I do a concavity chart. So this is f double prime. I have 1. I plugged in 0. I plugged in 2. I saw negative. I saw positive. That's changing concavity. Therefore, I have an inflection point. So since f double prime of x is less than 0 on negative infinity to 1, and f double prime of x is greater than 0 on 1 to infinity, I know the point 1, 2 is an inflection point. There are no vertical asymptotes for this graph. It's a polynomial. The end behavior is down, left, up, right. I know that because I have an odd degree and a positive leading coefficient. So now I can go ahead and sketch the information I have. I want to plot my inflection point, plot my relative minimum, plot my relative maximum, plot my y-intercept, which happens to be the relative maximum, plot my other x-intercept, and then draw in the curve with the correct end behavior. All right, try the next one. Again, answer all of the questions in the packet about this function, including doing the graph. Pause the video, unpause when you're ready to check. Okay, again, this is a polynomial, so the domain is all real numbers. It's very easy to factor. I can take out 3x cubed, so I get my x-intercepts of 0, 0, and -2, 0. That also gives me my y-intercept of 0, 0. My first derivative, just use our power rule, 12x cubed plus 18x squared. My second derivative, use the power rule again, 36x squared plus 36x. Find my critical values, so I set the first derivative equal to 0. I can factor out a 6x squared, set each of the factors equal to 0, and I get critical values of x equals 0 and x equals -3/2. For this problem, I just went ahead and did the first derivative test. So I made an increasing, decreasing chart with the first derivative. I plug in my critical value of -3/2 and then 0. I tested -2, -1, and +1, and I saw negative, positive, positive. So I know -3/2 is a relative minimum, 0 is not a relative minimum or maximum. Using my derivative speak, since f prime of x is less than 0 on -∞ to -3/2, and f prime of x is greater than 0 on -3/2 to 0, the point -3/2, -81/16 is a relative minimum. The reason why I underlined this is, again, we talked about this, I think 2 units ago, or 2 lessons ago, I mean. But just because these both came out to be positive, now again, in this case, because this is a polynomial, it would have been okay if I said -3/2 to infinity, but that's something you want to be careful about. So it's just a good habit to say -3/2 to 0 and just stop it there. There is no relative max, so I want to make sure to answer the question. Don't just leave things blank. Don't write 0, because that would be a different answer. So we write none. Possible points of inflection. Take our second derivative, which we did up here, factor out 36x, and I get 36x times x plus 1, set each factor equal to 0. I get possible points of inflection at x equals 0 and x equals -1. So now I do a concavity chart. So this is with the second derivative. I use my possible points of inflection. I tested -2, -1/2, and +1, and then I saw positive, negative, positive. Therefore, I have 2 points of inflection. Using my derivative speak, since f double prime of x is greater than 0 on -∞ to -1, and f double prime of x is less than 0 on -1 to 0, the point -1, -3 is an inflection point. And since f double prime of x is less than 0 on -1 to infinity, and f double prime of x is greater than 0 on 0 to infinity, the point 0, 0 is an inflection point. This was a polynomial again. It had an even degree and a positive leading coefficient, so the end behavior is up, up. There is no vertical asymptote because it's a polynomial. Plot the key points, your intercepts, your inflection points, or points. We have 2 of them. One of them happens to be an intercept also. And then our relative minimum. And then try to draw the curve the best you can. This one's it's a little tight in here. So just do the best you can. Next, I want you to try this one. Again, answer all of the questions, including doing the sketch. Pause the video, unpause when you're ready to check. All right, here we got a lot going on. This is a rational function now. It's not a polynomial. The derivatives are going to be a little bit more work. Our domain is -∞ to 2, 2 to infinity, so our domain is not all real numbers this time. We're going to have to pay attention to that. The range and the symmetry, that came from after I did the graph. So I'll come back to that after I get down to the graph part. X-intercepts, I have none. So to find x-intercepts, I set the numerator equal to 0. But if I try to solve this, I end up, it does not factor. And then I can see before I even finish, so I started to complete the square, and I can see that this is, because this is -4 plus 1, I would end up with complex solutions. So as soon as I see that, I can stop. I don't need to actually find them because they're not technically x-intercepts. They would be zeros if the question asked me for zeros, but it didn't. Y-intercept, plug in 0 for x, and I get 4 over -2, which is -2. All right, first derivative. Do the quotient rule. So we do bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. I'm going to multiply this out and then combine like terms. So this actually simplifies pretty nicely to y prime equals x squared minus 4x over the quantity x minus 2 squared. Do the second derivative. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Here I factored out an x minus 2 from the numerator, and then I reduced it with the denominator, and then I distributed in the numerator, combine like terms, and actually conveniently a lot of things cancel. So I end up with the second derivative is just 8 over x minus 2 cubed. All right, back to the first derivative. I want to find my critical values. So I set the numerator equal to 0, and I set the denominator equal to 0. I end up with x equals 0, x equals 4, and x equals 2. But remember, 2 is not within my domain, so technically that's not a critical value. However, when I do my increasing decreasing chart, it's critical that I put it on there because it tells me, or it'll help me with the test. And what I mean by that is, although in this case it didn't make a difference, 2 is not a critical value, but the function can change from increasing to decreasing or decreasing to increasing over an asymptote. And that's what's happening at 2. And so I don't want to get a false positive or a false negative on something being a relative minimum or maximum because I test something on the other side of an asymptote. So when I do my increasing and decreasing chart, I want to still put in the 0, the 2, and the 4 so that I know when I'm actually looking at 0, I don't plug in a value that's larger than 2 here. So I needed to plug in something between 0 and 2. So I picked -1 to the left of 0, 1 that's between 0 and 2, 3 that's between 2 and 4, and 5 that's greater than 4. Again, in this case, it wouldn't have made a difference, but I don't know that going in. So that's why I want to still put this here. And then also we see that we have a relative maximum and a relative minimum. So since f prime of x is greater than 0 on negative infinity to 0, and f prime of x is less than 0 on 0 to 2, the point 0, negative 2 is a relative max. Since f prime of x is less than 0 on 2 to 4, and f prime of x is greater than 0 on 4 to infinity, the point 46 is a relative min. Now I want to look for possible points of inflection. Well, I take my second derivative, set the numerator equal to 0 and the denominator equal to 0. 8 doesn't equal 0, so that doesn't do anything for me. And I end up with x equals 2 for a possible point of inflection. But again, that is not within my domain. Now, so at this point, I can stop. All right, that cannot be an inflection point because it's actually a vertical asymptote. However, I want to just show you. So if I did a concavity chart, notice that the concavity did change there, though. Okay, so one, that will help me with the graphing still. But two, that's just, again, something to be careful about. And even if a problem didn't ask you for the domain or for vertical asymptotes, you want to recognize that's not within the domain. So if I'm trying to find an inflection point, that is not an inflection point. Yes, concavity is going to change there, but this is not a place where the function exists. So we don't have any inflection points. We have a vertical asymptote at x equals 2. We are also going to have a slant asymptote, and I get that by doing synthetic division. So the slant asymptote is just the line y equals x. Now I go down here and I draw in my function. I draw the slant asymptote, I draw the vertical asymptote, I draw my relative maximum and my relative minimum. Those are going to be how I came up with the range. So remember I said earlier I'd come back to explain how I got the range. So I know this has to be the highest point on this piece because it is a relative maximum. This has to be the lowest point on this piece because it is a relative minimum. So the range is going to be negative infinity to this value and then this value to infinity. And I know what those values are because I found those points when I found my relative minimum and maximum. With regards to symmetry, I can see from my graph that this is not symmetrical to the origin and it is not symmetrical to the y-axis. So that's what I meant by that. I found on the graph there is no symmetry. There's one more problem. I want you to go ahead and do that, and then we will talk about this one on part 2. So I'm going to end this video here. This is part 1, and then we'll pick up the solution to this problem on part 2. But go ahead and do that now, and then start part 2.